Okay, wonderful. Um, Thank you very much. So, hello everyone. I'm Quentin. I'm very sorry for not being in the room with all of you. That would have been much simpler, but I couldn't make it, unfortunately. So, well, thanks to the organizer for letting me do this remotely, given the circumstances. I'll try to make it work. So I work for Google. I work on PKVM for ARM64, and this session is about physical memory allocation constraints for computational computing guests, which is a very complicated title, but what I actually want to talk about is problems, basically. This is not a session where I'll show a finalized design with a very polished implementation. I'm trying to convince you to take my patches. This intends to be like early engagement with the community to figure out how to address the problems. So the goal for this session for me was twofold. One is to raise awareness about those problems, so you have context when you see the patches, even though you might still hate them. And two, ideally to get some feedback from the community. So we'll see how easy that is given the remote setup here. But if we can do both of these things, it's fantastic. If we can do only the first one, that's already very useful, I believe. So I'm going to look at this from the PKVM angle because that's what I know best. But I think that the conclusions of the talk should be pretty much applicable to other type of computational computing solutions, hopefully. Yep. Oh no, I can. I'm not passing the slides. Can you see? Oh, is this? Can you see the next slide now? Oh wow, I can see in your there's like a 5 seconds delay. That's all right. So yeah, I'm going to talk about this from the PKVM angle. And I just wanted to start with a quick reminder about the PKVM page table setup in particular, because that's going to be very important for the rest of the discussion. So this is basically how KVM on all ARM CPU looks like. There's the host on the left-hand side of the picture, the guest is on the right-hand side, and at the bottom, running a hypervisor layer, there's the so-called world switch code, which is basically an extension of KVM that context switches between host and guest context. And the guest runs with what we call the stage-2 page table translation enabled, which does the guest physical address to physical address translation. Now we're going to spot the difference with the next slide. If it wants to load, wait for it. I hope you're ready. I clicked the button 5 seconds ago. Okay. No. There we go. So yeah, the difference with the previous slide is we have PKVM sitting at the bottom now instead of the world switch code. So it is the world switch code is very, very lenient, and it basically lets the host do pretty much anything that it wants. PKVM is far more opinionated about what the host should be allowed to do. And we now have stage-2 MMU enabled even in host context. And that is the foundation on top of which PKVM builds a confidential computing solution, because since PKVM has this stage-2 on the host that it controls, it can prevent it from accessing guest private pages and things like that. If we can, okay, the next slide is coming up a little bit quicker now. It's improving. So the guest stage-2 page tables are very boring because they look exactly the same in the PKVM context as they do in normal KVM. But the host stage-2 on the other end is actually interesting because it's a bit different. Everything into the host stage-2 is identity mapped. So the IPA equals the PA. And at boot time, the vast majority of the physical address space is owned by the host in PKVM parlance. It means it's accessible to the host. In fact, the host owns the entire PA space except the few regions where we have hypervisor data structures and sections and text and things like that. Because since the entire memory is ID mapped into the host, and the hypervisor is located in memory somewhere, we have to protect it from host accesses directly. Since we have very, very large portions of contiguous memory that we map into the host stage-2 page table, that allows us to basically use very aggressively bulk mappings. into the host stage 2. And if you look actually at the stage 2 page table, host stage 2 page table, right after boot, it consists mostly of gigabyte mappings covering pretty much the entire other space. The attributes of valid host stage 2 mappings are always defined in PKVM to be as weak as possible. And by weak, I mean weak in the sense of the stage 1, stage 2 aggregation rules that are defined by the ARM architecture. And the idea is essentially that to make the host stage 2 completely transparent to the host kernel, as long as it's well behaved. And so if the host wants to map something read-only, then it gets to decide. PKVM is not going to be opinionated. It just wants to remove access to certain pages. So after boot, we have a memory layout that looks a bit like the picture on the right, where we have mostly host-owned sections and a few PKVM sections in the middle. But things get a little bit more complicated, obviously, when we start running protected guest VMs. Because as a guest boots and as KVM handles the page faults for those guests, for the guests, then KVM will ask PKVM to say, hey, can you please donate this page to the guest? And that maps it into the guest stage 2, but that also happened to map it from the host stage 2. And when there's a gigabyte mapping in the host stage 2, when we want to remove one 4K page in the middle, we have no choice but to break the block to put an invalid mapping where the page has been donated. When a guest runs, there's two types of donations happening. There's obviously the host to guest's memory donation, but also host to hypervisor donations, because things like guest metadata or guest stage 2 page table pages themselves are allocated dynamically by the host kernel and donated to the hypervisor to run. One of the nice things we have though in PKVM is that whenever a guest gets torn down, the pages that have been donated to the guest and the hypervisor are reclaimed by the host, and we have a mechanism that allows to essentially coalesce the host stage 2 mapping back into large blocks to basically go back to the original state. And so we have, while the guest is running, there is some fragmentation going on into the host stage 2. And in the majority of cases, that's actually not a problem. We don't care all that much. It's not extremely visible in performance power and things like that. And in general, as long as the stage 2 mappings are larger than the stage 1, you're probably fine. And it's, basically generally things work well enough, but they work well enough. I think you see me coming until they don't. And in the mobile space in particular, there's lots of cases where it turns out that fragmenting the stage 2 is either kind of bad for power performance reason, but also just not possible in certain cases. That is due to the fact that we have a huge variability of hardware that we have to support. And because there's so much difference in the hardware, the symptoms that we get from host stage 2 fragmentation can be very, very different depending on the SoCs, for example. And it's actually quite likely, talk about that in a minute, but quite likely to magnify hardware bugs and things of that nature. So we have in real world seen problems around power and performance. We've seen things happening at the CPU level as well as DMA performance being impacted and things of that nature. And on top of that, we have more and more use cases that are pushing the boundaries of things we want to do in protected virtual machines in the mobile space. In addition to many additional constraints to this, it's very, very common on most sort of mobile SoCs to have a TrustZone, so-called secure world implementation that has very, very specific constraints in terms of, it requires physically contiguous memory to be passed to it. It's quite common for certain devices on the system to have limited addressing capabilities. Unfortunately, there is no such thing as a standard IOMMU in the ARM world. So we see all sorts of exotic IOMMU setups and things like that, which cause a lot of problems. So I want to spend a little bit of time to give you two examples of problems that we have found in the field to give you an idea of basically the type of thing that we're dealing with. The first example what's happening on a device that shall not be named, where we basically, by enabling PKVM, we saw a power regression in sort of lightly loaded use cases. That is particularly bad because on lightly loaded use cases, power is actually one of the primary things that we look at. Obviously, this is where you want to save power. And CPU performance was actually fine throughout the benchmarks. Light load as well as highly loaded scenarios was actually pretty much okay. It took quite some effort for the team to figure out what the hell was going on, because you probably would not expect a power aggression from these sort of things. But what we saw effectively was that whenever the stage 2 page table was getting fragmented, that was causing additional memory traffic due to the additional page table walks. For example, actually, interestingly, if you think about the hardware worker doing a stage 1 page table walk, there is a possibility in the absolute worst case that for each stage 1 page table you walk, you have to do a stage 2, a 3-level stage 2 page table walk. And so the number of memory accesses you have to do in order to resolve a stage 1 walk actually explodes quite a bit because of the enablement of the stage 2. And on this system, the frequency governor for the DSU, which is the DSU is the dynamic system unit, is the block on the SoC that includes the last level cache. The governor on the DSU was picking up that extra traffic, memory traffic, using some of the event counters that it has, and so that was tickling the governor just enough that it decided to raise frequency for the DSU in order to maintain essentially the throughput, and so that was causing the power regression we are seeing, which is kind of bad. The fixes, or let's say workarounds, that we have found in this case are of two natures. One is there was actually something where we were unnecessarily fragmenting the host stage 2 due to the way the tracking of memory shared with the secure world was done in PKVM. We were essentially fragmenting the host stage 2 in order to set software bits into the host stage 2 page table to say these pages have been shared with the secure world. By moving this tracking outside of the host stage 2, that allows us to keep the block mappings a bit more often. That solves one part of the problem. And the other part is the other mitigation, I would say. Whenever a guest is running, protected guest is running, involved a mix of using a CMA pool from which we were allocating the dynamically allocated hypervisor data structures, such as the guest stage 2 page tables and things like that. Instead of allocating them from system memory with get prepaid, we would do that from a CMA alloc operation essentially. And for guest memory, well, we implemented support for THP to back protected guest, which also helped a lot. But I'll come back to these things later on. Another interesting example I wanted to mention was actually we were seeing major impact on DMA performance whenever a protected guest VM was running, and for only one device on the system. It was not like throughout. This is one specific device on this SoC that was starting to misbehave due to protected guest VM running. The root cause is that essentially since PKVM aims to protect guest pages from the host, we obviously need to protect that on the CPU side, but we also need to protect the guest from DMA attacks. And in order to do that, it means that PKVM has to take ownership of the stage 2 IOMMUs and as well as the stage 2 CPU page tables, assuming there are stage 2 IOMMUs. If there's a single stage IOMMU, there are things that can be done as well, but I'm going to simplify the reasoning here. And the stage 2 IOMMUs in the PKVM world are actually surprisingly complicated. People from different architecture may not be used to that, but it's very, very common in the ARM world for IOMMUs to use page tables that have a completely different format from the CPU. And even for IOMMUs that actually have the same page table format as the CPU, such as the ARM SMMU, it's often very, very difficult to share the page table with the CPU for because of break-before-make requirements of the architecture and sort of inconsistency with how this is being dealt with from the CPU and device side. But yeah, basically what we were seeing was that by running protected VM, we had to fragment not just the CPU stage 2, but also the stage 2 IOMMU page tables. And that was, in the case of this particular device, magnifying essentially what was a hardware bug. And, and that's causing a pretty massive drop in DMA performance, which was pretty much unacceptable. The way to fix this problem was essentially pretty much the same as before. It was a mix of using CMA for hypervisor to back hypervisor allocation, as well as THP for guest memory allocations. Now that I've explained two of the sort of problems that we sometimes see with mobile SoCs, I also want to talk about the things that are coming up. Existing use cases of virtualization in the mobile space so far were mostly for transient, I would say transient virtual machines, where we would spawn a virtual machine, get it to do a piece of work, run for, I don't know, 30 seconds, a minute, something like that, and then would be torn down at the end of the execution. And as I've explained before, whenever the guest VM gets torn down, we're in a position actually to coalesce mappings back into blocks into the host stage 2 and things like that, which meant that if there is an overhead associated with fragmenting the host stage 2, that is actually just, that is temporary, which makes it a little bit less of a problem. But there's a push to have more and more services put into protected VMs on mobile phones, especially as we're trying to move things out of TrustZone and move them into virtual machines. We're going to have sort of always on VMs in Android. And when you're on a system where stage 2 fragmentation is really expensive, having a constant sort of steady state overhead associated with that is kind of not okay. And we need to find a better approach to that. THP is nice. It's proven to be extremely useful. It's also pretty unreliable in the sense that, especially on mobile phones that are memory constrained devices, there's no guarantee whatsoever that we will find huge pages to back a guest whenever it starts. And in the case of the always on VMs that I was mentioning, you could think that, well, actually you're starting this VM early on, so you're going to have plenty of huge pages in the system. So you're probably golden in this case. It's probably fine. But the reality is, because we're on mobile phones that are very memory constrained, we make extensive use of things like memory ballooning in the guest, so that every time a guest stops using, doesn't need a piece of memory, is going to use ballooning in order to relinquish those pages back to the host. And later on, whenever the memory request inside the guest increases, and we have to page the pages back in, there's no guarantee much later that we're going to actually find a THP to back that location. So there's a possibility that performance is just going to degrade over time, which is also not so good. Things like HTLBFS are just not really a thing for us. It's just way too expensive. Like, we can't carve out memory just for that, just for HTLB. And so far, virtualization on mobile space was mostly aimed at sort of high-end SoCs that sometimes have some of the problems I've explained are mostly fine, but also actually pushing towards the lower end of the SoC segments that have many of the problems I've discussed right before, such as limitations around memory that the secure world can accept, limited device averaging capabilities, weird IOMMUs, and things like that. It becomes a bit of the Wild West. All of that is a little bit complicated to deal with for us without having some way of constraining or controlling how physical memory is laid out to back a guest. And I'm going to pause right here on this particular topic and do a quick interlude on a different topic, and then I'll go back to the KVM stuff to talk about dmabuf heaps. So dmabuf heaps are building on top of the dmabuf abstraction. I think dmabufs are reasonably well-known object in the kernel. dmabuf is basically a file descriptor that is handled to an abstract buffer, basically an SD list. And then that file descriptor can be passed around between sort of kernel subsystems or over the kernel user space boundary. And the nice thing about dmabuf is that it allows to pass things around without copying. And that's particularly useful when multiple devices have to share a buffer, or when there is a pipeline of devices that need to access a buffer. For example, you're going to get the camera subsystem to put a frame into a buffer, and then that's going to get passed to the GPU, and then that's going to get passed to the TPU, and then that's going to get passed to the secure world and things like that. These are very, very common pipelines of devices we see in mobile space. dmabuf heaps are probably a little bit less known, but they're basically an IOTL interface to user space that lets user space allocate dmabufs. The idea is that a dmabuf heap is basically a small kernel driver that exposes a file to user space. So you have an example on the right-hand side of the picture about the dmabuf heaps we have on a Pixel 6 device. Don't ask me what I do. I have absolutely no idea, but there's plenty of them. It's a popular thing in the mobile world. And the idea is basically that those kernel driver register themselves as dmabuf heaps. And so that allows user space to talk to them with a standardized IOTL interface to say, can you please give me an allocation? And the driver that is on the back of that heap is allowed to create that dmabuf from whatever it wants. So it can be done, it can allocate from memory from the system heap if it wants to. It can allocate memory from CMA, so it can be global CMA pool or a reserved CMA pool specifically for this driver. It can also, it's a driver, so it can take ownership of just a reserved memory region in the system, like a NOMAD region or something like that. Or it can have arbitrary custom allocators behind. The idea of dmabuf heap is that user space is kind of one of the weird things I would say about this API, but that's actually quite interesting. User space is responsible essentially for allocating the right type of memory to pass down a device pipeline. The reasoning behind this is that very often when you have 3 or 4 devices that need to access a buffer in a pipeline, one of them may have a weird constraint. It's like extremely common for mobile to have something like that. And it's actually really difficult in the kernel to know about this pipeline ahead of time. And so the idea is that in cases like that, user space is going to be in charge of allocating a dmabuf from a heap, from a known heap that meets all the requirements of the devices in the pipeline, and then user space will be passing the driver around. And so that's how dmabuf heaps basically work. It's a standardized interface that gives user space access to specialized memory allocators. Now, with that, I'll probably see where I'm going now. We can go back to the KVM problem I was mentioning earlier on, and about how do we express essentially memory allocation constraints for backing KVM guests. In KVM, I'm not talking about PKVM here, but in KVM, it's user space's responsibility to do the memory allocation in general. We have the set user memory region IOTL, or the new version for guest_memfd, where basically user space says, okay, this part of guest memory is going to be backed by this. And I think that in this context, dmabuf heaps are actually an incredibly powerful tool to provide user space with a way of expressing memory allocation constraint, because you can, if you know that you're on a system that has this or this problem, you can just go and allocate the type of buffer that meets the requirement, and then use that to pass that to the guest VM. When a heap makes a dmabuf mappable, that's a property of the dmabuf exporter. It's actually reasonably easy to back standard guest memory, non-protected guest memory with a dmabuf. Because this is basically mapped, and in fact, KVM will be pretty happy with this. It's going to look, it's basically going to be a PFN map mapping resolution into the memory abort path, which is not uncommon. And in fact, I just for fun before the preparing this slide deck, I tried to run a very primitive guest, very primitive guest from a CMA allocated region. And that seemed to be working just fine. So this is probably just works as is basically for KVM. But for PKVM and confidential computing in particular, this is a little bit harder because obviously in confidential computing, KVM is far more opinionated about the backing store of pages that are being donated to a guest. And so the question that I really wanted to put out there and that I was hoping to discuss with the community today, and that's pretty much almost the end of my presentation here, is how do we reconcile the needs that we have in the mobile space to have, in certain cases, some control about how physical memory is laid out when backing guest memory? How do we reconcile this with the guest MFD idea of having this very, very specific backing store and allowing only that for confidential computing? I have one last slide to give some high-level ideas. I also did not mention the, let's say, short-term band aid that we intend to have in Android for that. I'm happy to talk about it if you'd like, but I don't think it's very, very applicable to upstream. But I have a few ideas here, high-level ideas that are intended to start a discussion, really. First one being that we could essentially extend the set user memory region to IOTOL, which accepts file descriptors, to also accept dmabuf file descriptors. And in this case, KVM would become a dmabuf importer. It's actually quite, when we're looking at it, quite interesting from the coding side, because whenever you want to import a dmabuf, you have to call into the dmabuf core. And the operation of importing a dmabuf is very much centered around the struct device. And I think in order to do this, we would probably have to allocate the struct device per guest. And then there's a question about, should we want to basically put the stage-2 manipulation helpers as DMA hubs, which effectively would basically amount to saying a guest is a virtual device that has an IOMMU that's actually a stage-2 CPU MMU, and whenever we admit import the dmabuf into this virtual device, that DMA map operation that is initiated by the dmabuf heap core ends up calling this the KVM sort of page table manipulation logic. I think it's an interesting idea to think about. There's a question obviously about how do we enforce the mmap semantics that we want to have for confidential computing with that. And then another idea would be to have a completely new thing that allows to convert a dmabuf into a guest MFD. I haven't looked in detail about how this could work, but this idea is basically inspired by the udmabuf driver that we have upstream, which it's a different type of conversion, kind of the other way around. It goes from a MFD to a dmabuf FD. But perhaps we could essentially construct a guest MFD, actually correct guest MFD object based on the dmabuf. I'm not completely sure if that's sufficient to enforce mmap semantics, and that's the point where I stop talking and opening up for discussion and hopefully get great ideas from all of you guys. Thank you all. So I cannot hear the room. I just want to mention that. If someone has a question, that'd be great to have a microphone or something. All right. Thank you very much. Goodbye.